is an example from Spotify, how we should use data processing. It's very simplified, but in this case you can see that, for example, we get in streams from users, so we have large log files containing streams. Just that in this example we can have timestamp, track, and artist tuples for every stream. From this, in the next step, we would create an aggregate of how many streams we have per artist. And after that, we can possibly just select the top 10 artists for a specific time period and output that into a database, which would then be used to serve clients where people request top lists, for example. So, like the naive approach to how to solve this problem is illustrated here in a simple Python script. So we would have this input streams, which would be just logs that we use with what people stream. This aggregate artist method would then take this as input and create an output, which would be like artist streams. So how it actually does this is unimportant for this argument, but in the second step we would calculate the top artists based on this previous step. And it would be very similar. So we have an input, which is the output from the previous step, and we create a new output, which would be the top artists. And then in the last step, we would take this data from the top artists and we would export that into a database. So this is a way of sort of structuring our data processing. Instead of just having one large script, you would split it up into chunks. So there are a few problems with this. I mean, some things that you always have to do when you do these kinds of data processing. So let's say that our first step, the first step when we aggregate on an artist level how many streams you have, if that would fail, or we would get some garbled data because the process crashed that was creating it, then we want to, of course, clean up the data so no one uses this broken data set. So you would have to do something like this traditionally, where you would catch exceptions and clean up the data after yourself. Then there is a second scenario which would happen often is that, let's say that your second step in your data processing chain crashes. Then you fix your code and you want to rerun, but you don't want to repeat the first step, which worked fine. So you would have to test existence of the previous steps before you run them. So if they already exist, you want to skip those steps. So this is like a typical thing that you would do in the pre-Luigi world. A third scenario is that, like most of our data processing steps, we want to run those every day. So we want to run these entire pipelines where we create top lists or reports or stuff every day, and we want to parameterize the output on the date. So we have a complete history of everything that we've run every day for the last year or something. So this code would then grow into something like this, where we create like the last week's worth of data based in a loop, and we just parameterize the output. So this isn't horrible. I mean, the code is okay. The problem is that at Spotify we have thousands of these sort of data processing pipelines that we run every day, and it gets very repetitive to rewrite all these things every day. And it's easy to make mistakes, and you have errors all the time. So to solve this, we've created this framework to make this easier, called Luigi. So Luigi has a few core features. It has a Python-based interface for creating these data flows, or like defining these data flows and actually running them. It has an emphasis on Hadoop and HDFS integration, so there is an entire like Python-based file system wrapper for the Hadoop distributed file system. It's based around atomic file operations, so anything that you write to disk is not actually available to any other tasks until you actually close your file. And a few more features. I will show you later during the presentation. So let's go back to our example with this top list that we were creating. In Luigi, you would define your first task something like this. So in Luigi, there is a base class in Python called task, and it essentially has three required methods that you want to override. You have output, which specifies which output this task writes. In this case, we want to write some to some file in the Hadoop distributed file system called HDFS. And this would be artist streams.tsv in this file. This task itself would require another dataset called streams, which is also defined as a Luigi task outside of this scope. And then we have a simple run method, which can simply access the input, which is implicitly defined as the output of all the requirements. And then it can also, of course, access the output and write results out of that. You would then be able to call this through the command line by simply running luigi.run inside of your Python script, which we will see here. So you would just write Python dataflow.py, if that's whatever your Python file with the dataflow definition is it. And then you would specify the task name of the task that you want to run. This would print something like this out to your command line interface. It will first check if Aggregate Artist exists. If it doesn't exist, as in this case, then we'll check if the requirements exist, which would be streams. And when it's checked all the requirements, it will start to actually schedule running all the tasks. In this case, it will run Aggregate Artist, and then it will be done in exit. The next time you would run this, if you would run it immediately afterwards, it will not run anything, because in the first step it will check if Aggregate Artist exists, and it will already exist, so nothing will be run. So this is sort of similar to tools like Makefile, or if you've used Hadoop previously, Uzi or Azkaban. But we think it's a much slicker interface, and it makes for some really quick development, especially as we are a Python-heavy company. It's very useful for us to have a framework for this in Python. Something that we're using a lot in Luigi is we're utilizing the object-oriented nature of Python and how this task class can be subclassed. So you can essentially create template tasks based on task, where you override the run method of a base task, and then you let people implement other methods on top of these instead, to simplify some data flow, typical data flow tools. So Luigi has a few pre-implemented tasks that we ship with Luigi. We'll probably split these out into modules as Luigi starts growing, but like the core features would be Hadoop MapReduce framework that's using Python. So you can implement MapReduce jobs using Python in a very simple way, which I will show you in a minute. It allows you to run Hive and Pig queries on top of Hadoop, which are like SQL-like languages where you can query data from your Hadoop cluster. And we also have some basic support for Postgres, working on support for Cassandra as well, since that's heavily used at Spotify. So I will just quickly go over how the Hadoop framework inside of the MapReduce framework inside of Luigi works. It has if you've ever written a MapReduce job in Java, you know that doing something as simple as doing a word count, or in this case an artist aggregation, will take you like a couple of hundred lines of code, standard Java world. And in Luigi, it's like the opposite. It's super simple to write something like that in Luigi. While you have the full power of MapReduce and you can do anything manually, as opposed to a language like Pig or Hive, it has very little boilerplate compared to Java. It has a few features which are sort of Hadoop specific, but for example, it will fetch any arrow logs from the Hadoop cluster after you run a job. So if you run this, you run some distributed script on top of your Hadoop cluster, and it crashes on, let's say, 20 out of 200 machines, then Luigi will actually fetch back the arrow logs from those 20 machines and send those back to your terminal, so you don't actually have to jump to a bunch of different hosts to check out the arrow logs. So this is what our Aggregate Artists class would look like in Luigi, actually implemented as a MapReduce job. Just let me go over the basics of a MapReduce job. You have a mapper, you have a reducer. The mapper will essentially allow you to send the key data on a specific key based on something in the input data. And the reducer will get all the data associated with one key and lets you aggregate stuff based on that key and the values that you send to that key. So in this case, it's sort of like a standard Luigi task as I showed you before. We specify requires, it's still streams, and we specify output, it's still like a file in HDFS, which is artiststreams.tsv. But in this case, we haven't implemented a run method. Instead, we have implemented the mapper and reducer method, and the run method is implemented by the new base class that we're using here, which is Luigi Hadoop job task. And behind that run method, there is a lot of logic, but that's, for you as a user of Luigi, that's entirely abstracted away. So you only implement these very simple mapper and reducer things. So in the mapper, in this case, we would just say that we extract the artist, and we say, for every line that in the input, we take the artist and so we say there is one stream for this artist. And then in the reducer, we will get all of these one streams in for every artist, and we just output the sum of the streams as the total amount of the streams for that artist. To complete our top list example, this would be a possible second step in that chain. We would, in this case, require aggregate artist, which is the previous step that we defined, and we will output it, in this case, a local target, which is a local file on our machine, which would contain the top 10 artists. And the run method isn't really important, but as you can see, we just open up the input file. It's treated as a regular Python file object. There's nothing special about it, and then you just write to the output file. Then in the last step, we would utilize Luigi's built-in Postgres support. In this case, we inherit from the Postgres copy to table class, where you don't even have to specify any output. There is like a shortcut in this class where you simply specify the credentials of the Postgres database and table that you want to write to. You specify the columns that your input file contains and which data types these have. And if the table doesn't exist, Luigi will create it for you. So it's very easy to use and set up new tables with data. And then you just specify the requirements. So everything that's in the requires will be used as input and put into this database table. So let's say that if we were to run all of this, it would look something like this. We schedule the artist top list to database, which is the last step. That's what we want to accomplish. When we schedule that, as before, Luigi will first check if that exists. In this case, it will not exist, so it will check the dependencies, and then the dependencies of the dependencies, and so on. And eventually, it will start running stuff. As soon as it's scheduled everything, it will start running things in the correct order. So it will first run aggregate artists, then the top 10 artists, and then lastly, it will run the export to the database, and then it will be done. So this is what will be written to your command line, but I mean, it's not really giving you an overview, especially it's not really human readable. So in Luigi, we have this lightweight daemon, which actually receives notifications of everything that's happening with your data pipelines that you run on any machine in your data processing cluster. So there's a simple web interface where you can see exactly which tasks are being run, which has run before, and which have failed, and which are going to run in the future. So in our example, we can see here that streams exist, that's our input file. We have run aggregate users successfully. We're currently running top 10 artists, and we will, just as that finishes, we will run artist top list to database. And here we can see the results with some bogus data. So Luigi can handle quite big dependency graphs. The one that I showed you previously, the example, it doesn't really split up or join stuff together, but this is actually taken from the Spotify production Luigi data pipeline. And as you can see, there are quite a lot of interdependencies between graphs. At any given time, we have something like 5,000 different tasks being dependent on each other, being scheduled. And we run stuff hourly and daily. Data processing is huge at Spotify. So this is how it could look. As you can see, sort of up in the left corner, there is a red little box, which means that that task has failed. So that can happen because input data can be broken, especially when you're dealing with these kinds of amounts of data. It's easy that input data is broken, or that someone submits a bad patch. Someone drops the database or something. Shit breaks. So we built in some error notification stuff in Luigi as well. By default, you will get emails. Whenever a task fails, you will get an email with a Python traceback of exactly what the error was. And if this was actually run on a cluster as part of a MapReduce job, it will have fetched the logs from that cluster and send those in an email to you. So you will actually get the exact error that has occurred. In this case, we can see that I just messed up the name of a variable, so misspelled streams, and here we go. We have an error email saying exactly what the error was. So in the beginning, I was also talking about this parameterization thing, where you want to run something daily. To solve this in Luigi, we have introduced this magic variables inside of Luigi tasks called parameters. So you simply define parameters on your Luigi task, and these are magic variables that will implicitly